Hello, class. Today's lesson is on the last major application of integrals, which is finding volumes of solids. And there are a lot of ways in which we do this. There's four main concepts in this chapter. The three that we will be covering for Calculus AB are finding solids with known cross-sections, which is what we're going to do today with this video. Our next major task will be using the disk method. And then the third major task will be using the washer method. And these are all methods of finding volumes of three-dimensional solids. So I'll just go ahead and start right away. Today's main concept are finding volumes of solids with known cross-sections. In other words, like if you were to take a solid and slice it, do a cross-section, cut it in half somewhere in the middle, what would that cross-section look like? And we use those cross-sections to find volumes. So basically, we will be taking three-dimensional shapes. So this is going to require a lot of visualization on your part, having to really think what it would look like. Whose bases, we're going to be taking three-dimensional shapes whose bases are quote-unquote sitting, for lack of a better word, on the XY plane, or are flat on the XY plane. So for example, this three-dimensional shape is a triangular prism, and if you look at its base as a triangle, that's laying or sitting on the XY plane. So we'll begin with that. Then we'll be taking cross-sections that are either perpendicular to the x-axis so the cross-sections will either be perpendicular to the x-axis, as this picture is showing here. This cross-section of a square is perpendicular to the x-axis. So perpendicular to the x-axis, I want you to always visualize, are like books on a bookshelf. Meaning they're stacked horizontally. So imagine, if you will, I have this pile of CDs right here. When they're perpendicular to the x-axis, they'd be stacked like this, or here this is how I'm looking at it. They'd be stacked like this. So you would integrate from left to right. Each cross section is the shape of a square, and I'm basically accumulating all the squares as they're stacked perpendicular to the x-axis. So they're stacked from top to bottom, and you would sum them up from left to right. So they're stacked vertically from top to bottom, and you would sum up all these areas from left to right, and it creates a three-dimensional shape. Like this three-dimensional shape right here is a rectangular prism. It has a length, a width, and a height. So it's a rectangular prism. It's a three-dimensional solid because I took all these two-dimensional planes or squares, stacked them up like books on a bookshelf, summed up all those areas from left to right, and that creates a volume. So that's what it means when your cross-sections are perpendicular to the x-axis. Or sometimes the cross-sections will be perpendicular to the y-axis. And so you can think of that as like papers in a pile. So that would look more like this, just like that, papers in a pile. So a side view would be like this. So now they're sort of stacked vertically. So you would total them up from bottom to top. And they would be going long ways, I guess you could say. So instead of being stacked like this, or excuse me, like that as before, now they're stacked like this. And you would sum them up from bottom to top, and they would be stacked like this, like papers in a pile. Okay? So that's the difference between perpendicular to the x-axis versus perpendicular to the y-axis. And so again, the volume will be the accumulation. So there's that word accumulation again, which means an integral. The accumulation of all the areas of all the cross sections from a point A to a point B. So the volume will equal the integral from a point A to a point B of all the areas of all the cross sections. It'll either be like this. This is if it's perpendicular to the x-axis. Or it'll be like this if it's perpendicular to the y-axis. So in other words, if it's perpendicular to the x-axis, like books on a bookshelf, you integrate with respect to x. If it's perpendicular to the y-axis, like papers in a pile, you integrate with respect to the y-axis. Okay, so let's go ahead and try example 1. So example 1 is taking the same shape as our sort of generic example right here, and now we're going to look and see how we would do this to find the volume of the shape. Well, the first thing I want you to recognize is that we have a known geometric formula for this shape. So in practice, we would not use this method on a shape as simple as this, but when we teach you a new concept, we like to begin with something familiar to show you how you would do the process with something more complicated. So first thing, we'll just look and see what the actual volume is. So for the actual volume, we can simply use the known formula for a triangular prism. And that is 1/3 times the area of the base times the height. So we can basically see that the area of a base is a square, a 6x6 square. So the area of the base is 6 times 6, which is 36. We can see from the fact that it goes from 0 to 10, or it shows us right here, that the height is 10. So the actual volume is just 1/3 times 36 times 10, which would just be 360 divided by 3, which is just 120 cubic units. Okay, so in practice, this is how you'd find the volume. Very, very simple process. But to teach you how to do this volume by cross sections, we're going to use this simple shape to show you how it works. Okay, so this is how the first thing we would do is we would need to find what the cross sections are. So it says find the volume of the pyramid shown below whose base is a square with a side of 6 feet and a height of 10 feet. If you look at the picture, if you were to slice through the middle of this, like take a saw and just slice through the middle, what you would see is it has the cross section of a square. And another thing you might notice is that the squares are either bigger or smaller depending on where you make that cross section. So imagine my CDs that are stacked like books on a bookshelf. So they're perpendicular to the x-axis. You can kind of see that here. They're straight up and down. They're stacked like books on a bookshelf. And And they depend on, I guess, the width, you could say, of this pyramid. And so right here, they have a nice little picture for us. This is kind of, they called this S. And then here's X. So X is going, of course, left to right. But the side of the square is going top to bottom. And so what we're going to try and do, because first of all, we realize that the area of the cross-section is the area of a square. Which is basically just side squared. And what we need to do is get that side in terms of X. Because we're going to be integrating with respect to X. So I'm going to use this very helpful picture to get the side length in terms of X. But one thing I want you to notice is that the side length of this square is going to be 2 of these S's. S plus S would be the side of one whole square. So this is going to equal 2S squared based on this picture that was given to us. And I'm going to use this picture to set up a ratio of similar triangles. Okay, because I have that this little side is X and this little side is S, whereas the whole long side is 10 and this whole big side is 3. So I can basically say that S is to X, this base is to that height, as 3, the bigger base, is to 10, the bigger height. And then with some cross multiplying, I can get S in terms of X, which is important. I need to get the side in terms of means get S alone and have X in your answer. That's what it means to get S in terms of X. Okay, and so the area of the square is going to be 2 of those S's squared. So it's going to be 2 of these, 2 times 3/10 X squared. So that's just 3/5 X squared, which turns into 9X squared over 25. So right there, that's the area of each cross-section with respect to X. So this will be smaller when X is shorter, and the further out you move on the X-axis, the bigger the side of the square would be, and so the bigger the area of the square. And then the volume is you would just sum up all those areas from 0 all the way up to 10. So we just accumulate all these areas from 0 to 10, which means we find the antiderivative of this. So you just take the constant multiple 9/25 times x cubed over 3, and we'll evaluate that from 0 to 10. Well, the 3 and the 9 will cancel. So you'll have 3/25 x cubed. You evaluate it from 0 to 10. So that ends up being 10 cubed is 1,000. So it ends up being 3,000 divided by 25, and then minus 0, because if you plug 0 in there, you just get 0. And then that ends up being 120, just like we got up here when we just used the formula. So again, in practice, if I was asked to find the volume of a triangular pyramid, I would simply use this formula. Okay, I would not go to all this work. It's just we want to show you here with a simple example how this process works. So let me recap. I had to figure out what the cross section was. It's a square. So then I had to remember the formula for the area of a square, which is side squared. But then I had to figure out how I could write the length of that side in terms of the variable x. So I used this picture to get the length of the side, which was 2 of these little s's. The length of that side in terms of x. So we used the similar triangle ratios to get side s in terms of x, and then I basically plugged this here into the formula. So it's 2 of these sides squared, and so this here was the formula for the area of each one of these squares, which is going to depend on x. It's not the same area every time. Sometimes it's small, sometimes it's big, depending on where x is. So this is the formula for that area in terms of x. Plug in an x, value here, and you would get the area of that square that's right on that x value. Now the volume is when you accumulate all of those different areas from the beginning of the shape to the end of the shape. So from 0 to 10 in this case, and then we just integrate like normal. Okay, so that's example 1. Let's go ahead and move on to example 2. So with example 2, they didn't give us a picture. We might want to draw that picture because the more you can visualize, the better your chances will be of getting it right. So it says the base of a solid is a region enclosed by a triangle. So that'll be our base that's sitting on the XY plane. Whose vertices are 0, 0, 4, 0, and 0, 2. Let's go ahead and sketch that. So I have vertices on 0, 0, 4, 0, and 0, 2. Okay, so there's our region enclosed by this triangle. And I'll go ahead and just sort of lightly shade that in. Okay. The cross sections are semicircles. So these are going to be the cross sections here, and they're perpendicular to the x-axis. So remember, that's like books on a bookshelf. So they're going like this. Now imagine these are standing up, by the way. Okay. And as you can see, depending on where x is, the semicircles will be larger, and they sort of get smaller as you go from 0 to 4. Okay, so first thing we notice is that the area of each cross section is going to equal half the area of a circle. So 1/2 pi r squared. Also notice that the diameter of each semicircle is limited by this line. The diameter can only go as high as this line is right here. So also notice that the diameter, which by the way is double the radius, I'll just put equals 2r in parentheses, is limited by the line. And so let's get the equation of the line, which is really easy to do. The y-intercept is right here. It's 0, 2. And the slope is just rise over run. So it went down 2 and to the right 4. Wait. So it's like 1, 2, 3, 4. So the slope was rise over run. So this line is y is equal to mx plus b, negative 1/2 x plus 2. And the diameter is limited by that line. So basically, the diameter, which is 2 times the radius, is equal to negative 1/2 x plus 2. The reason why that's so important is because I need to get this area in terms of x. Okay, so then the radius, I would just divide everything by 2. The radius is just going to be half the distance from the x-axis to this line, so it just would be half this equation here, so negative 1/4 x plus 1. So then the area of each cross-section is basically going to be 1/2 times pi times that radius, negative 1/4 x plus 1 all squared. And then the volume is going to be the integral from 0 to 4. So I'm accumulating from the beginning of the shape to the end of the shape, from 0 to 4. The sum of all of those areas, the 1/2 pi times negative 1/4 x plus 1 quantity squared dx. Okay, I'm totally running out of room. So let's just solve this one using a calculator. Oh, and tilde us too right here. Woohoo! I love when they tell me to do that. Using a calculator, which means I'll just do FNINT. So let me plug that in right now. So I'll go to Math 9. And then I'll type in my equation for the area of the cross section, which was right here. It was the 1/2 pi, I'll just call it 0.5 pi, times, parentheses, negative 1/4, I'll just call it negative 0.25 x plus 1 quantity squared, because that was the radius squared. So it was 1/2 pi, oh wait, sorry, right here, 1/2 pi r, which was negative 1/4 x plus 1 squared. And we're integrating with respect to x, and we're going from 0 to 4. So we end up with approximately 2.094. So let's take the answer to this, and I'm going to write it over here. So volume ends up equaling approximately 2.094 units cubed, because it never gave us what units. I just know that it's cubed because we're talking about volume. And then I'll just put by FNINT. Okay, so that was example 2. Let's go ahead and look at example 3, which is going to be a little bit more complicated, but I think you can handle it. You might need to watch this one a couple of times. So let's just go through nice and slow. Okay, so they give us the base of the solid, which is the thing sitting, quote, quote, on the XY plane. So that's flat on the plane, and the other things are standing up. And that shape is an ellipse. So it might help. Okay, also, so before I move on, sorry. The cross sections are perpendicular to the x-axis. So we're going to be integrating with respect to x. So it might help us to solve for x. Solve in terms of x. Get y in terms of x. So because it's going to be perpendicular to the x-axis, we're going to want to get y in terms of x, meaning get y alone and have x in the answer. So I'm going to take this equation and do that. So I've got x squared over 4 plus y squared over 25 equals 1. That's the equation of this ellipse. So as you can see, it has a center at 0, 0, and then because the 4 is under x, it goes left 2 and right 2. And the 25 is under y, so it goes up 5, down 5. Little review of conic sections. But let's solve for y and get it in terms of x. So first I'm going to subtract the x term to the other side. And then multiply by 25. And then square root both sides. Okay, so this will come in handy later. So save for later. Okay, so then it says the cross sections, these are the things standing up that are stacked like books on a bookshelf, are isosceles, which is very helpful. It's going to be very helpful to us. And they're right triangles. This is awesome. They're isosceles right triangles whose hypotenuses are on the ellipse, which is important that we understand that. The hypotenuses are on the ellipse. So the cross sections are perpendicular to the x-axis. They're isosceles right triangles whose hypotenuses are on the ellipse. Find the volume of the solid. Okay, but before I find the volume of the solid, I have to find the area of each one of these isosceles triangles in terms of x. So let's just first consider the area of a triangle, of any triangle. That's equal to 1/2 base times height. The super awesome, amazing thing about these triangles is they're isosceles, meaning their two legs are equal, and they're right triangles. So it kind of is hard to see because the right angle, you know, it's standing up. They're trying to draw it 3 dimensions. It's hard to do that. So let's look at this shape in a way that will help make more sense. So it's a right triangle, and it's isosceles, so the two legs are equivalent, and the hypotenuse is what's lying flat on the ellipse. So if you look at this particular isosceles right triangle, so the area of this isosceles right triangle is basically going to be 1/2 times base, which is A, times height, which is A. So the cool thing about this particular triangle is that the base equals A equals the height. They're all equal to A, so it's very helpful. Okay, so the area of this particular triangle is equal to 1/2 A squared. I just need to get that A in terms of x. So I need to get this in terms of x. Which will prove to be a little challenging. So let's think very carefully about this picture. Notice, first of all, the hypotenuse is split in half. Okay? So half of the hypotenuse is limited to this expression, because if you solve for y, so let's just look at the top half of the ellipse. The top half of the ellipse would be the positive square root of 25 times the quantity 1 minus x squared over 4. That is the equation for the top half of the ellipse. And so half of the hypotenuse is limited by that equation. It can only go as high as the ellipse goes. And this is the equation that describes how high the ellipse goes. So I'm going to have to first get A in terms of the hypotenuse, and then that will help me get A in terms of x. So if you look at this isosceles triangle, okay, if I used Pythagorean theorem, that would show me that a squared plus a squared is equal to the hypotenuse squared. Okay? Now remember, the hypotenuse is 2 of these. So maybe I should say that first. The hypotenuse would be 2 of these positive square roots. Because half of it, the top half, is the positive square root. If I just simply double that, that would get me down here as well. That would get me that full length. So the sum of the squares of the two legs is equal to the square of the hypotenuse, and this is the hypotenuse right here. So it would be equal to this whole thing squared. Okay? So what that shows me is that 2a squared is equal to 4 times 25 times 1 minus x squared over 4. So that shows me that a squared would be 2 times 25 times 1 minus x squared over 4. And if I simplify that a little further, I get 50 times 1 minus x squared over 4. That's what a squared is. This is wonderful because now I can just say, all right, well, the area of these triangles is just 1/2 of this. 1/2 a squared. Since I'm running out of room, let's move this on the back. So now I can say the area of each triangle in terms of x is equal to 1/2 times 50 times 1 minus x squared over 4. Make sure I got that right. So there's a squared, and the area of the triangle was 1/2 a squared. So I just take half of that. So basically it's 25 times 1 minus x squared over 4. Okay, the hardest part has been done. Now to find the volume, you just sum up all of those isosceles triangles from the left to the right, from -2 to 2. Because we're stacking them vertically, so some of these triangles are going to be ginormous, depending on where they were. And some of them will be tiny, depending on where they were. Okay? But there's going to be a bunch of these triangles, and we're stacking them from left to right because they were perpendicular to the x-axis, so like books on a bookshelf, from -2 to 2. So I'm going to integrate this from -2 to 2 of the area of each triangle, which we found was 25 times, here, I'll go ahead and distribute the 25. So it's 25 minus 25x squared over 4 dx. That'll make it a little easier to integrate if I can think of it as the difference of two functions instead of the product of two functions. Okay, so then I just go ahead and integrate piece by piece. So it's 25x minus 25/4 times x cubed over 3, and integrate that from -2 to 2. So that's 25x minus 25x squared over 12 from -2 to 2. So that's 50 minus 25 times 8 over 12. I'll simplify that in a second. Minus -50 minus 25 times 8 all over 12. Okay, so then I get, first of all, let me simplify these a little bit. So that would become a 2, and that would become a 3. And I'll have 50 plus 50, so that'll be 100. And then minus 50/3. Okay, I think this should have become positive somehow. Oh, because this is cubed. Whoopsie. This is cubed. So when you cube a negative, it stays negative, so this would become positive. And then I'm subtracting it, so then it becomes negative, another -50/3. So think of this as 100 minus 1/3 of 100, which would basically be 2/3 of 100, or 200 over 3 units cubed. Okay, so that was our last example, our most difficult example. And I want you to, at home, go ahead and try the U-try. That's this one here. So I want you to pause the video and try and find the volume of this three-dimensional shape whose base is a parabola that's sitting on the XY plane and whose cross sections are squares. So pause the video here, and then we'll check your answer in a bit. Okay, hopefully you took a minute to try this on your own. I'll go ahead and sum up with you. Basically, the area of each square is side squared, and half the side of each square is a square root of x. So each side would be 2 square roots of x. So the area is basically 2 square roots of x squared, or 4x. So the volume would be the sum from 0 to 4 of 4x dx, and that ends up equaling 32. Hopefully you got that one right, and I will see you in class on Thursday. And if you have any questions, please come see me in tutorial.